Hi, today's lesson is 7-6, exponential functions. This is what the exponential function looks like. Y equals a times b to the power of x. Now you're used to the linear function, y equals mx plus b. This is just a little bit different, but it still has similarities. The first letter here, a, that represents a number, that is going to be your starting value or your y-intercept when x is equal to 0. Okay, that's our starting value. The b is representing our constant factor of change. Can't spell today. So if you think about something that you already know, like the linear function, you know that the b represented our y-intercept. And this m was our slope, or our constant change. So the exponential function has the same parts, it's just that they look a little bit different. Okay? So again, our a, our first number, that's our starting value, or our y-intercept. And the second number, the b here, that's going to be our constant factor of change. So let's take a look at some examples so that you guys can understand what this means. This function will be given to you on the MCA on your formula sheet. There are two types of exponential functions. There's an exponential growth function, and there's an exponential decay function. They look very similar, don't they? Now remember, it's y equals a times b to the power of x. So here we have our a, and here we have our b. The 10. Remember, that's our y-intercept. That's where our function starts. When x equals 0, y is 10. Now if I were to plug in x is 0 up into this function, 2 to the 0 power is 1, and 1 times 10 is 10. Let's plug in some more points here. X is 1, 2, 3, and 4. Let's see what happens. Now if I plug in 1 for x, 2 to the first power is 2, times 10, that's 20. If I plug in 2, 2 to the second power is 4, and 4 times 10 is 40. If I plug in 3, 2 to the third power is 8, times 10 is 80. Do you notice what's happening here? Do you see a pattern? Now remember, I told you that the b, that was your factor of change. So if you see this 2, that means that the change that's happening is multiplied by 2. Doubling, times 2, times 2, times 2, times 2. So my next number here would be 160. So it looks like we start at 10 when x is 0, and then we're doubling every single time. Our factor of change is to multiply by 2 every single time. So times 2, times 2, times 2. So let's go ahead and graph this and see what it looks like. 0, 10, over 1 up 20, over 2 up 40, over 3 up 80, and then the other point is off the graph. So you see this nice exponential curve going up. That's exponential growth. Let's look at decay. So again, my function starts at 10. When x is 0, y is 10. That's your y-intercept. Again, if I were to take the x equals 0 and put it up here, 1/2 to the 0 power is 1, and 10 times 1 is 10. Let's plug in some more points here. Now if I say that x is 1 and plug in 1 up here, 1/2 to the first power is 1/2, and half of 10 is 5. Now, again, this right here is my factor of change. It's 1/2. So I'm multiplying by 1/2. Times 1/2, times 1/2, times 1/2, times 1/2. What happens when you multiply by 1/2? You take half of something. You cut it in two, right? So what is half of 10? It's 5. What is half of 5? It's 2.5. What is half of 2.5? 1.25, right? It's going to continue going on just like that. You know. Okay, now let's graph it. 0, 10. Over 1 up 5. Over 2 up 2.5. 3, 1.25. So here, if I connect the points, you can see that we have a decay, an exponential decay. So if you notice here, the b, which is our growth or a factor of change, we can see here that when it's a number that's bigger than 1, it's going to be growth. And if it's a number that's smaller than 1, like a fraction here that's less than 1, it's going to be decay. And that's something that we can always notice. So let's take a look at our first example. For this first example, we can see that the function is going to start or have a y-intercept at 0.25 or 1/4. So if I go over here to fill up my table, when x is 0, y is going to be 0.25. So let's plug in a few more numbers for x. Now what I could do is use a calculator, plug in x is 1, 3 to the first power times 0.25 in the calculator and see what the y value is. However, you know that this number right here tells us our constant change. It's 3. It's times 3. So that means that this is going to go times 3, times 3, times 3. That's what our pattern is going to look like, a constant times 3 pattern. So we could just fill this out just knowing that. I could say, okay, what's 0.25 times 3? And then continue the pattern. Times 3 again, times 3 again, times 3 again, you know, and fill it out just like that. Then I can go over here to graph it. Now, because this number is bigger than 1, we should see exponential growth. So 0, 0.25, over 1, up 0.75, over 2, 2.25, over 3, all the way up to 6.75, and then if I go over to 4, it's a big jump here up to 20. So we can see this really nice curve, exponential growth, just like that. So again, our intercept is at 0.25, and our growth, our constant growth, is times 3, times 3, times 3. All right, number 2. Look at our exponential function. You can see it starts at 20. There's our y-intercept. So y-intercept, when x is 0, y is 20. And then if you notice that the number here that's in our factor of change, it's 1/2. Anything less than 1 means it's going to be exponential decay. So our constant rate of change, or constant pattern here, is going to be multiply by 1/2. Multiply by 1/2. Okay? See the multiplication? Over and over and over times 1/2. So if I go ahead and start filling up my table, 1, 2, 3, 4, I know that this change, this constant change, is going to be multiplying by 1/2. And you know that when you multiply by 1/2, half of 10, half of 5, half of 2.25, right? It's the same thing as dividing by 2. Okay? So let's go ahead and fill out our table. Or sorry, we just filled out our table. Let's go ahead and graph. Okay, so 0, 20, 0, 20, 1, 10, over 1 up 10, halfway. Again, we're cutting in half again, and we're cutting in half again, and we're cutting in half again. So we see this nice exponential decay going on. Okay? All right, number 3, we're going to label each table as either linear or exponential. So let's take a look at what's happening in each table. Here in this table, I see that the function starts or has a y-intercept of 0, 2. And then if you take a look at the pattern, it goes +4, +4, +4. It's a constant addition pattern. Take a look at the x. It goes up plus 1, plus 1, plus 1. So when we have a constant pattern that's addition, this is a linear function. So let's write the rule. Y equals mx plus b. We know that our constant change is our slope. Looks like we have plus 4 over plus 1. 4 over 1, or 4. And then our y-intercept is right here. That's where the function starts. That's 2. So my rule for this table would be y equals 4 times x plus 2. If I take x, multiply it by 4, and add 2, I get across the table. Multiply it by 4, add 2. Multiply it by 4, add 2. You see how it works? That's linear. Looking at this table, I can see that my y-intercept is at negative 1. Now, if I take a look at the pattern, it is times 3, times 3, times 3. It's a constant multiplication pattern, which means it's exponential. Let's write the function rule. A times b to the power of x. Now remember that the a, this first number right here, this is where the function starts, the y-intercept, which is at negative 1. And the second number here is the factor of change, the constant multiplication, which is times 3. So this is the exponential function for the table. Here in example number 4, you see that I have 4 tables. And I'm asking you to write the exponential function rule for each table. And remember that looks like this. Y equals a times b to the power of x. Remember our a is our starting value, our y-intercept, and b is our factor of change. So maybe you want to pause the video and try and see if you can write the function rule for each table. So what I did here is I just wrote down y equals a times b to the power of x, just with little boxes. So I'm just going to fill in the boxes for each one. So let's first figure out, where does the function start? What is the y-intercept? Looks like in this one it's 2. So that's where the 2 goes. Then the second number, the b here, that's the constant change. And it's always multiplication. What am I multiplying by? What am I constantly multiplying by to get to the next number? It looks like times 7, times 7, times 7. So that's where the 7 goes. So y equals 2 times 7 to the power of x. There's my exponential function. Let's look at the second one here. Function starts at 64. When x is 0, y is 64. Now let's take a look at what we're multiplying by. The numbers are getting smaller. Now you might see this as divide by 2, divide by 2, divide by 2, divide by 2. But if I put a 2 right here, it's going to look like I'm multiplying by 2 over and over and over. It has to be multiplication. So even though I'm dividing by 2, I have to think, what's that the same as multiplying by? It's the same as multiplying by 1/2. Times 1/2, times 1/2, times 1/2. So I put 1/2 here. If this is decaying, if this is going down, this number is going to be less than 1. And I can see that that's 1/2. Okay, let's go to the next one. Function starts when x is 0, y is 5. Now let's go ahead and take a look at the pattern. Looks like we're multiplying by 3. My constant change is multiplying by 3, so this is multiplied by 3. And the last one, function starts when x is 0 at 7, times 2, times 2, times 2. It's a constant multiplication of 2. So you see how these are different? Even though this is divide by 2, we look at it as, what are we multiplying by? Half. Okay? Here this is growing. It's double, 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 doubling, so times 2. So there we have our 4 exponential functions that are representing the tables. It looks like each one of these 3 are exponential growth. And this one is the exponential decay, because this number is less than 1. Okay, in class we watched a video for the McDonald's penny a day scenario. So we're just going to see if we can use that scenario and write an exponential function. Remember, if I make a table of what's happening, on day 1, McDonald's will pay you 1 penny. On day 2, they double it and pay you 2 pennies. On day 3, they double that and pay you 4 pennies. On day 4, they double again and pay you 8 pennies. So what's the exponential function that models this scenario? Y equals A times B to the power of X. So we have to look at what is the y-intercept. And remember, that's when x is 0. So we have to go back to x here and see, well, the function starts when x is 0. So we have to back this up. I can see that the pattern is to double, multiply by 2, multiply by 2. So I have to back it up. That means divide by 2, divide by 2. Well, what's 1 divided by 2? You're right, that's 1/2. So the function starts at 1/2, or the y-intercept is at 1/2. So I'm going to put 1/2 right here. Now this is the factor of change. What's happening? Every single time to get the pattern, I double it, multiply by 2. So here, this would be times 2. So this would be my exponential function for the McDonald's penny a day scenario. Number 6, we have the ice bucket challenge. Starts with one person completing the challenge, and then they challenge 3 friends to do the same thing. So in order to write an exponential function for what's happening, I first need to start off with a table. On day 1, day 2, day 3, day 4, and so on, what's happening? On day 1, one person does the challenge. On day 2, remember that one person is challenging 3 friends, so 3 people do the challenge. On day 3, 9 people, because remember each of these 3 people are challenging 3 people. And then on day 4, 27, and it would continue just like that. So in order to write the function rule, you need to figure out what's the y-intercept. Where does this function start? And it always starts when x is 0. So if this is going times 3 every single time, the pattern, to back it up, I would have to divide by 3, divide by 3, divide by 3. What's 1 divided by 3? Yep, 1/3. So let's write the function rule. Y equals, the y-intercept is right here at 1/3. This is the factor of change. Times 3 times 3 times 3. There goes the 3 to the power of x. And this would be the function rule that models the ice bucket challenge. Number 7, let's say here we have a rumor. It started with one person knowing a secret, and each day they tell 5 people. The day after that, each of those 5 people tell 5 more people, and so on. So again, if I'm going to write an exponential function, I need to first start with a table. Day 1, 2, 3, 4, and so on. On day 1, one person knows the secret. The next day, they tell 5 people. The next day, those 5 people each tell 5 people. Now 25 people know the secret. The next day, they each tell 5 people. Now 125 people know the secret. So how do I write an exponential function for this? I have to go back to when x is 0. So do you see the pattern? It's multiply by 5 each time. So then you go back, divide by 5, divide by 5, divide by 5. 1 divided by 5 is 1/5. Now let's write the function rule. Y equals, the first number in the function is the y-intercept, which is 1/5. This number here, the b, that's your factor of change. That's multiplying by 5 each time, so that's the 5 and to the power of x. So this function rule would represent the scenario of the rumor being started. And that's all we have here, lesson 7-6. Have a great day.